Welcome to ExplainerCast, episode 14. I'm your host, Dave Smith.
And this is Shane Swenson.
And we have some explaining to do. Today, we're going to explain a very common household device that many people have now, but prior to 2014, no one had, and that is called Alexa.
Nice.
Today, we're going to tell you how these little devices work, what they do. Are they spying on you? Which is like the first question people always ask me about these things. And it's coming from a place of experience as both end users of the device and, for me at least, as an engineer who worked on it for about 4 years. A couple of years after it came out, I spent 4 years working on the Alexa project at Amazon. So I'm going to share with you some of the fun things that make Alexa interesting and some of the technology that powers it.
Very cool. So this will be the insider's journey then.
Yeah, exactly. Yeah, it should be fun. I don't know. Should we just jump into it, Shane?
Yeah, let's go.
Okay, first, a segue from the saga that we've been bringing to you about telecommunications really lands us here. All the technology and innovation that has been developed is a great segue to Alexa because it is totally built on a lot of these internet technologies we've been talking about so far, specifically TCP, which enables so much of what Alexa is able to do, but of course, necessary but not sufficient. There's a lot more too as well, but pretty much everything you do with an Alexa device involves TCP packets.
Yeah. And so, just to recap, the internet is this giant network that connects all these computers and devices around the world. And each of those devices has an address, essentially what's called an internet protocol or IP address. And there's a slight lie in that, but let's go with it. And the internet protocol allows them to send individual messages to each other. And then TCP allows them to essentially have more like extended conversations over that messaging system. And that's, again, how the data that's transferred, I assume, between the Alexa and the computers that are providing the service Alexa delivers to take place. And maybe that's one of the key things we'll talk about, Dave, is what actually happens in the device, the Echo or whatever, the individual device hosting that application on the client side, like in my house, versus what other network services is it using to perform the functions that we ask of them.
Yeah, exactly. And we'll definitely walk into that. So why don't we start with that? And I think the best way to explain this is to describe a day in the life of a user who speaks to a little Echo device. And it looks like, actually, we should start with a trigger warning.
Yes, indeed.
Right?
We probably already blew it, but okay, let's go.
Yes. Why don't you give us the trigger warning, Shane?
Yeah, so as you probably already noticed, if you have a voice assistant whose wake word is the one we've been using throughout this conversation, it's probably going to be problematic. So I guess we could apply a code name or we could just go with it. What do you think, Dave?
I say we just go with it. Put your headphones in.
Yep.
Press the mute button on your Echo devices if you have one. Listen, no one listens to these things out loud anyway. It would be too publicly embarrassing to admit that you listen to our show, so everyone puts headphones in.
Exactly. Yeah, this is a... Yes. And I guess the other thing to say is, while we don't necessarily have as much insider information into the voice assistants provided by Apple and by Google and some of the other major vendors, each of which have their own default wake words, we could expect that at some level, they're going to operate in a very similar fashion to what we're describing today.
Yeah, very, very likely. Although, just as a little caveat, definitely this world is changing with the introduction of large language models and generative AI over the last year when it really hit the scene publicly. And I no longer have inside information at Alexa, and none of the information we share today will be inside or proprietary information.
Okay.
I've actually gone to great lengths to get trained on what is and isn't allowed to be said publicly about the Alexa product. But definitely everything we say to you is going to be, not everything, but much of what powers Alexa's brains today is getting revisited right now. I can almost guarantee it.
Yeah.
Okay.
And it's just to talk about that, there's really two big trends. One of them is the amount of computation that can be performed in an endpoint device, whether it's one of these standalone devices or the voice assistant in your phone or other mobile device. That has been going up significantly. So you can do more work, call it at the edge or client side. And then the other is this tremendous innovation in these machine learning trained models to perform voice understanding and synthesis, as well as text and information manipulation in a more and more sort of human way. Like you said, over the last year has really been growing. And I would guess most of that's today happening in the servers, but some of that will be migrating to the edge devices over time as well.
Absolutely. Okay, so let's jump into it. When you walk up to one of these little Echo devices, which, by the way, came out 10 years ago this year, if you can believe that.
Oh,
It was
nice.
November 6th of 2014. Very, very hard to imagine it's already been 10 years.
Yeah.
When you walk up to one of these devices and you say the wake word, which by default on an Alexa device is the word Alexa, what's happening is that little device has a microphone array that is listening only for that word. That's it. It doesn't actually record audio or send any information to any servers until it captures that word. And probably a little known fact is that it actually does have like an 8-second buffer of audio that's saved on the device, because you have to put information into memory before you can analyze it. So the question is, well, how much information? And the answer, at least when I was there, was about 8 seconds. And so there's a little 8-second sliding window of audio that's being stored on the device all the time and then immediately purged, analyzing for the waveform that looks like Alexa. And that is the most compute intensive thing that's happening on this little Echo device. And bear in mind,
continuously analyzing that, as you said, the sound waves essentially hitting the microphone for that specific pattern and all the variations it could take.
Yeah, exactly. Some people say, Alexa, and it works really well. In fact, there's a little bit of machine learning happening on the device, not training, but just recognition of that wake word. That's how that's all built. So there's a tiny bit of speech recognition, tiny bit of word identification, and of course, there's actually multiple different wake words or phrases that you can configure it to use, but you can't make your own. And the reason you can't make your own is because there have been specifically trained machine learning models that identify the wake word, and it would cost Amazon a ton of money if everyone could submit their own and they had to do the compute to train new models for any arbitrary text. So they had like 3 at the time.
And that's something I could see changing actually fairly soon, because I can picture some technologies now that would allow you to fingerprint the wake word and kind of generalize it and enable more flexibility there as an example of things that'll likely happen in the near, at least in the next couple of years.
The Echo devices are actually running, you might be wondering, like, what kind of hardware and software are on them? Well, they are just little computers, these Echo devices. They're low-power CPUs. The early ones could be, the early smallest versions, the Echo Dot Generation 2, could actually be powered by a USB cable. So, very low wattage required.
Yep.
And they're just running little CPUs, and they run the same operating system that a lot of the other Amazon products run, like Fire OS, which is a modified version of the Android operating system, which is the same operating system that powers many, many smartphones, which under the hood is using an operating system called Linux. And so they are just little Linux computers listening for audio. That's all they do. Then, I want to kind of talk about what happens when you say the magic wake word. What happens next? Well, once someone actually says the magic wake word, there's software on the device that has identified that happened. It lights up the little ring on the device to say, okay, I'm listening now, and it opens an internet connection to an Amazon server to begin streaming the next thing you say to the Amazon servers. And I say streaming specifically because it's audio, right? So it's not just like a single request and response where you say, okay, I caught everything. It's not like you type a sentence in a text message and then hit send, right? It's actually real-time audio, and the device needs to know, when should I stop listening? Like, how do I know the user has finished speaking their command or question? And the answer is
quick question.
Yeah,
actually, before you answer that, does it also use some of that 8-second buffer to send any of the context before the wake word, or is the wake word like the start of what it's sending?
Yeah, the wake word is the start of what it sends.
Okay.
The Alexa, as a program and by policy, has no interest in collecting any additional audio.
Okay.
Not the least of which reason is because it's actually very expensive to store that much audio, if you can imagine how many people are all using these products.
So it starts at the wake word, and now, like you said, it's capturing the sound waves, digitizing them, turning them into numbers that can then be replayed as sound later. And then I assume sending those every some fraction of a second, sending over individual messages with the updates.
Yep, exactly, in little bundles. And in fact, I'm not totally sure about this, but I think it was actually using HTTP2. Actually, I think it was using SPDY, SPDY, which is like a precursor of HTTP2, to do streaming data sent to the server over TCP. Or actually, maybe it was over UDP. I can't remember now.
Yeah, I was almost wondering if I were building it And again, that sounds like what someone who builds web services would do. If I were building it, I would also consider treating it just like a voice over IP telephony session and just using like the VoIP encapsulation. But again, either one will work.
Yeah, they both work. There are advantages to not using voice over IP. The first one is firewall restrictions. You know, HTTP, and in this case, HTTPS is so ubiquitous.
Yeah.
If you want to maximize for just, the quote, just works principle, then you really want to use a protocol that is very likely allowed by every device that connects a user's home to the internet, or even a corporate world too.
Yeah, and you'll be hitting other HTTP APIs as well, so this just makes all that traffic look about the same. Makes sense.
Exactly. So as soon as a wake word is spoken, this audio starts to stream over HTTP to a server. Well, what server is it going to? And the answer to that is a very big, very expensive server in a fleet of servers that performs a service called automatic speech recognition, or ASR for short. And ASR is the process by which you take spoken audio and convert it to the textual representation. And this is done through machine learning models. And this really is the secret sauce that made Alexa, and frankly, all voice assistants, start working about 10 years ago, where really reliable at scale ASR came onto the scene. And it was and still to this day remains a very compute and memory intensive process to take this audio and turn it into text. And the way that works is that machine learning models have been trained on chunks of audio as input with output as literally just text, like typed text. So if I record an audio of me saying, "What is the weather today?" the textual transcription of that is the word "what," then "is," then "the," then "weather," then "today." So that's like 5 words written out. And that is literally all these ASR systems do. They just take that and they translate it into text. And this takes a ton of CPU. And probably becoming less and less as we have more machine learning specific hardware that can do like matrix math really fast. GPUs probably help with this. But at the time I was there, it was just big CPU computers, and lots of them, because you can imagine there's a whole bunch of people in the world all speaking to Alexa at the same time. And so every single one of those speech streams needs to be independently processed from the others. And so you can imagine just a fleet of servers that handle all of that audio.
Yeah, and this needs to be real time. Like, you can't save it for later and process later, because 2 things. Number 1, we're human beings and we're impatient. We want our answer quickly. But number 2, you promised that we're going to figure out when to stop recording and stop sending this data over. And I assume that this process plays into that as well.
It does. And that process is called endpointing, which is the algorithm by which the ASR system determines, yes, the user is probably done saying everything they want to say. And this is a good segue into how these ASR models work. And this is what I'm about to describe next is actually pretty general knowledge on how ASR works in general. But there are 2 kinds of models that inform how the system can determine what the text is. One of them is called a language model, which is where we say, okay, if I see the word weather, well, that can be spelled 2 different ways. Which spelling is the more likely one that the user intended? And that's informed by a model called a language model, which has been trained not on the spoken audio files, but actually on written text, so that it knows that when I say "what is the weather," the word "weather" in that context probably means WEATHER, meaning the climate.
Yeah.
Whereas if I had said, "Alexa, whether you like eggs or ham, I have a riddle for you," it's like, okay, that's a totally different context.
Yeah.
WHETHER. So homophones are a big problem, and the language model is what solves that problem. And they do really, really good at it.
So homophones meaning homo meaning same, phone meaning sound. So these are words that sound the same but have different meanings and even different spellings in some cases. But the computer has to understand through the semantic layer, which means the meaning of these words and the context that surrounds them, how to resolve that.
And what's really interesting is these language models, they don't actually know anything about English or language. They just know what words are more likely to follow other words, or even in the middle of a sequence of words, if there's an ambiguity, here's how it's probably spelled. And this gets really complicated with a lot of other things that I'll go into in a minute when we get to what's called entity identification, which is where you've got named things or people or places.
Yeah.
How the heck do you spell some of these things? And I'll get to that in a minute.
Okay. But just to segue here, Dave, I think this is part of where these became viable about a decade ago, because we've been trying to do speech to text for, since at least the 90s. I was trying to use software that would do speech to text, and it was terrible because it was only looking at the phonetic or the sound layer, and plus the algorithms were probably written a lot by hand or trained on very small data sets.
Yeah.
And so they just weren't that accurate. You would try to speak as carefully as you possibly could, and they would still make all kinds of mistakes. And I've noticed this over time. Like when I'm driving, I might use my phone's, speech to text to do something. And it used to be, the accuracy is clearly going up over time. And now even the accuracy of capitalization and punctuation.
Yes.
And sometimes if you're watching it, don't do this while you're driving, but talk to your phone in speech to text mode and watch it go back and change words you already said as it figures out what the right choice was based on what you said later. It's really cool to see how much information is being integrated to produce correct text from speech.
Yeah, it's really, really cool. Okay, so I mentioned that there were two main models that power ASR, and I started with the language model, but in reality, that's the one that runs second. The first model that has to run takes the actual sound content and turns it into text candidates. And not just text candidates, but actually what we call phonemes, where these are, for any given language, these are the unique set of sounds that can be made by the human mouth. So forget the alphabet. It's not A through Z. We're talking like the sound, V. It's like a voiced B sound kind of, or the sound ow, or, even the letter A in English can be pronounced ah, a, right? And so these sounds we make have names and labels, and they're called phonemes. And this model that identifies those phonemes from the speech that was given to it is called the acoustic model. And it operates by looking at the acoustic data that comes through the sound file and turns that into discrete phonemes. And then those phonemes can be then translated into actual in-language words. Yeah. And so acoustic model to phonemes, phonemes to words. And by the way, each one of these is producing not just one answer, but multiple, because, it knows the word weather could be spelled two different ways. And so those are both candidates.
Yeah. And there's ambiguity at the acoustic layer as well. So I imagine you produce multiple phonetic candidates and then downstream multiple language candidates as well.
Yep, exactly.
Yeah, like thinking about like in English, like, the letter B as in Bravo versus the letter V as in Victor, over in a noisy room, just alone, you would hardly be able to tell the difference. But then from context and what comes after it, you figure out which one it was.
Yep, exactly. So all this stuff gets pieced together, and the output really is just a simple piece of text. What is the weather? Just as you would expect it to be written.
Yeah.
But like I said before, it's actually candidates where you would have alternate interpretations of the audio, each with a confidence number attached to it between 0 and 1. And we call these things in the machine learning world hypotheses. And this tripped me up for a little while because I'm like, wait a minute, it's not a hypothesis. But when you think about it, this is kind of a humble take on machine learning. It's like the machine says, I hypothesize that what you said was, what is the weather? With a confidence of 90%. It's like, okay, great. But I also hypothesized that you said bat is the feather, It's like with a confidence of 20%. It's like, that is my second hypothesis. And so sometimes the second hypothesis is actually the correct one. Right. And that's a really challenging situation. And Alexa had all kinds of systems to help figure that out that would process downstream information to try to re-rank some of those. Suffice it to say that the final output of the ASR system is the text of what the user spoke.
Right. Or the most likely text. And sometimes these things make mistakes and we catch them. Dave, I think this is one of those technology areas that either is changing or will change. I think some of these newer language models, especially those that are called multimodal, meaning they can interact with different modes, like not just typed text, but also spoken language and maybe even visual, optical character recognition. They're combining all of these, call it inference steps, into a single model, as opposed to a phonetic layer and then a language layer and then a semantic layer. And that's part of what's increasing their fidelity, but at the cost of yet higher demand of computation. And so it'll be interesting to see if we can tell as users that these models are becoming more sophisticated behind the scenes.
Yeah, it will be. That is very interesting. Today, at least with Alexa, these are separate systems, and we'll get to the understanding side later, which is what comes next. But before we go there, I want to say that Alexa actually speaks lots of languages. And
Sure.
you can even configure Alexa to be multilingual, but only 2 languages at once, which is kind of interesting. You have to tell it, I speak Spanish and English. And that's because we don't have yet, at least at the time I was there, a merged ASR model that can interpret any of the supported languages. But we did have some models that could do 2. And when you think about the permutations of that, like it's very challenging. Like imagine building a machine that could handle even mixed language. Like I could say half of my sentence in English and the second half in Spanish, and it could actually understand that and create the correct text. Like very, very challenging.
Yep.
But
yeah, that's an area,
It's
again,
pretty cool.
I could see these large language models that do integrate more languages and the translation between them having potential to expand that capability over time.
Yeah, for sure. So let's move on in the next step. So all of this that I just described happened in less than a second. And that's necessary because you want this thing to respond to you pretty quickly. But there is more that needs to happen. And that is, the next thing is, well, okay, now Alexa knows the text of what you said, but what does it mean? What does the user actually want Alexa to do? And so let's just go with the what is the weather today example. So what is the weather today? Well, now we need a system that can take that text and understand what the user wants Alexa to do. And that is called natural language understanding or natural understanding, which is just the idea that you can take spoken language and turn it into an understanding that a computer can execute. And in the case of a computer, we need to know, hey, look, Alexa has like 500 different things that it can do. Which one is this? Or is it any of them? Because it can also be the case that someone asks Alexa to do something that it simply can't do.
Yep.
But in this case, asking for the weather is something that it can do. And so this system, natural language understanding system, is responsible for taking the phrase, what is the weather today, and then picking from this list of hundreds and hundreds of different intentions that the user may have and saying, aha, it's this one. It's the get the weather intention. That is what they want.
Right.
But where? What weather? Well, now we need context information that comes from the device that accompanies the speech that says, hey, I'm a device and I'm located in Salt Lake City, Utah. And it's like, okay, well, from that, now I know I can go to a weather service, I can pull the information, and I can go get it. But that's not this particular component we're talking about, this language understanding side. Its job is simply to understand that the user wants the weather. Then, after that, it gets passed down to another system that actually goes and fetches that information. And I want to go there next, but before we get there, I want to dwell on the language understanding side of things a little bit first. This is also a very challenging thing to do in the same way that ASR is challenging, and that is that the input space is enormous. There are so many different ways to ask for the weather. I can say, what is the weather today? I can say, hey, what's the weather going to be today? I can say, is it going to rain today? A lot of different ways to get there. Not as many.
You could also add
ways.
a time and a place, right? You could say, what's the weather going to be tonight or in a different city?
Exactly. So all of these things are attributes of what the natural language system has to understand. And so those also get encoded. So it says, all right, the user's intent is get the weather. The city that they're looking for is called X, and the time that they're looking for is Y. And these are values that then need to become the output of the natural language understanding system.
Mm-hmm.
So that some other system can then go, oh, okay, well, my job is just to take a get weather intent and the city name and time and just provide that information back to the user. Very, very straightforward, actually, compared to the language understanding. So how would you build a language understanding system? Well, it turns out that this has actually been technologically one of the underdeveloped sides of the language processing world for many, many years, until really just recently with large language models. Prior to large language models, there were lots of different machine learning techniques, and all of them were just okay. They were just so okay enough, in fact, that most of these digital assistants would actually hard code thousands of different wordings that people could use to ask for the same thing. So much so that the majority of commands or questions that people give to Alexa devices actually were exact string matched to already entered by a human text that matched exactly what they said. So like when I say, what is the weather today, guaranteed there's an entry in a database somewhere that got matched to, rather than going into some kind of advanced machine learning system to figure out what that meant.
Right. And that makes sense too, that these started as, and I remember some of the early like natural language systems, they were very narrowly scoped in the domain that they could operate in. So they like,
Yes.
I remember one just about like flight reservations, or just, yeah, about weather is another good example. And essentially it was so that it was possible to essentially enumerate all the possible queries you might make and how to properly respond to them. And obviously that requires a lot of work, and it's going to be always limited by what you can afford to set up by hand compared to something much more general.
Yes, and when you have a small number of domains, it's actually pretty straightforward to build this. And that's exactly what happened with Alexa. In 2014, when it launched, I think it only had 3 or 4 domains, and they were play music, weather, and I think maybe reminders or something, or timers. No, timers is what it was.
Yeah.
Yeah, and it was just basically those 3 things. Oh, and the fourth one was you could ask questions about the music that was playing. Like you could say, what song is this, or what artist is this?
Okay. And again, discrete data that's already available to look up.
Very discrete data we had, and also very easy to parse the text of the speech and turn it into action, because it's a very limited domain. It's like, if you said something like, how many inches are in a yard, it would just be like, I don't know how to answer that. Like, that's not music, timers, weather, or, asking
That's actually a great one
music.
too. Cause do you mean the unit of measurement? Do you mean your front yard, your backyard? There's a lot of
Yeah, exactly.
language is hard.
It is very, very hard. So every domain that was added to Alexa complicated its ability to understand natural language and necessitated more advanced techniques that actually did use machine learning and statistical methods for understanding. But even then, it just got harder and harder and harder. Because think about the effect of adding a 5th domain. Like, let's say you add shopping. And now suddenly I can give commands to ask Alexa to buy something for me on Amazon or check the price of something. And it's like, oh boy, how easy would it be to confuse a question about the price of something with a question about some music that happens to be playing at the moment?
Yeah.
The answer is very easy. And this kind of domain confusion was a major, major engineering challenge to try to help it grow. And over the time that I was there, I think we had well over 100 domains. And so this whole process became very, very challenging. You can just imagine the test suites that had to be created to make sure that there wasn't confounding questions that could turn into different domains.
Yeah, there's kind of a hidden, what we would maybe call an n-squared problem, where each time you add a new domain, you have to deconflict it against all the existing ones, which increases the cost of each new one in proportion to the size of the set.
Exactly. So every new domain is not just incremental cost, it's a lot more.
Yeah.
This is a lot to chase down, and especially when you have all of these manually entered rules with fixed text, like I was saying before.
Yep.
Which, even in that case, you go, well, this text might actually have a meaning in this new domain, even though it was originally meant for weather,
Yeah.
And of course, my mind blanks when I try to think of examples, but it makes sense that one command in one domain could very well apply in another domain.
Yeah, and we humans, we reuse words across domains so much. So, yeah, like a shower could be the fixture in your bathroom. It could be the action you take after you've gotten dirty. It also could be that it's going to rain later in the weather context. So, and then the next thing, and you mentioned this already, is now when I imagine localizing all of these domains into all of the supported languages and the differences in idioms. So in English, maybe that's the set of ambiguities for the word shower, but in a different language, they might have other places where the same word is used, but not in, but they might also be split. And so like the domains are going to intersect and interact in different ways, potentially in different languages as well. And yeah, that sounds like a very complicated problem to keep working on.
It was. It wasn't super my problem to solve, thankfully.
Yeah.
But it was something that a lot of people worked on. Okay, so let's now assume that this natural language understanding system is functioning as designed. It correctly identifies the user's intent. It correctly identified all the entities. Now what? Well, oh, no, I have to add one more thing before we go on. There's one more important part.
Okay.
The way that you spell things when written and the way that you pronounce things when spoken are often in conflict with each other and also easily confusable, even within one domain. So for example, here's a great example. You can say something like, play music by U2. Well, U2 there's an artist called U2. It's a letter U and then digit 2. But
Yep.
also, YOU for you and
Yep.
TOO for 2 is a perfectly valid interpretation. And so,
As is YOUTWO if you're speaking to a pair of people.
Yes, exactly. So how do you figure out which one is which? Well, this is where entity recognition comes in. So one of the jobs of both the ASR system and the natural language understanding system is to house catalogs, hundreds and thousands of different names of entities that could be confused by their phonemes. So like U2 is a great example. When ASR is doing its work, it needs to know that when you say play music by U2, you probably mean the artist. You probably don't mean either of the other two options that Shane just listed. And so that needs to be there. So that's one challenge with entity recognition. Another challenge is that sometimes we do non-standard spelling. So like, for example, there's an artist called Keisha, and the way this artist spells their name is KE$HA. And it's like, when you go to search a music catalog, it needs to be spelled that way because it doesn't exist the other way in the music catalog.
Right.
And so the natural language understanding system has to know that the ASR system will probably not cover all of those, and it will produce the phonetic spellings of some of these words, and it needs to know how to convert those into the actual written spelling form.
So you have like a mapping or something to fix it up?
Exactly. Yeah, so we had a couple different ways to do that. One was just with big catalogs of things, and the other was actually like handwritten, manually entered mappings
Rules?
Exactly, of how things were spelled versus how they were spoken. And I have the claim to fame of making it work for the phrase Les Mis. When you want to play music from the musical Les Mis, it really did not handle that well, and I was the one who entered the fix so that you can say play Les Mis, and it would actually play Les Miserables in the catalog.
Yep.
So
nice.
You're welcome, world. That's the only thing I did that was probably useful to anyone.
All right. Well, I'm going to go try that later today just to see if it still works.
Yeah, good call. Okay, so moving on from natural language understanding, we've identified the intent, we've identified the entities, we have actual like entity IDs for these things, like this is artist U2 with ID 12345 in the Amazon Music catalog. Now, what do we actually do to play it? Well, now there's a system within Alexa that knows how to dispatch these commands to other components that are really actually other Alexa servers living on the back end that know how to do these different tasks. And we'll start with music, but then we'll cover weather as well because they're both different enough that I think it's worth mentioning. So with music, a system needs to be invoked to say, hey, here's a user, they have an Amazon Music Unlimited account, or they have a Spotify account, or they have a free trial of Apple Music, or whatever it is. I need you to play this song on that service, and here's the IDs for all that stuff. Well, what that service now does, or what that music system does, is it actually sends a command back to the Echo device. We finally, in this huge chain, we're actually sending a command back to the Echo device that says, hey, play this song right now using this account. Or actually, it doesn't even say play the song. It starts streaming audio directly to the device so the device can start playing it. Now, there's some nuance there on whether the service actually pushes audio or whether it pushes like a URL that the device can pull for itself.
That's what I was wondering.
Yeah, and I think it's actually the latter. The device is actually pulling audio from a well-known URL so that it can do things like buffer a few seconds in advance or handle play and pause requests right on the device, things like that.
Yep.
Yeah, so the long and short of it is that the music service first validates that the user can even do that, and in some cases, like, actually, you don't have a Spotify account, so you can't play this music on Spotify. Sorry. That's the answer. And that itself is also a command that gets sent back down to the device to say, look, tell the user they can't play this music. And we'll get to that in just a minute. So, but in the happy path, when it actually works and the user's authorized, then the music URL goes back down to the device, and the device has logic coded into it so that it knows how to download music from a URL, authenticate the user, whatever it needs to do, and actually play those songs.
Yeah. So, I mean, it's a full-fledged music player. You're just prompting it through voice, and then the server that's doing the voice and language and entity recognition is helping to tell the device what you want it to do next, which is to play the music.
Yep, exactly. And, now before we get to how weather works, let's say what happens if there's a song playing on the device and someone says the wake word. Well, the device has to be smart enough to pause the music or at least reduce the volume in the music, turn on the microphones and listen for the next command, and smart enough to know that the next command probably means that the music needs to be paused right now and not play. And this is something that not all digital assistants do very well. Some digital assistants will actually not pause the music. They'll hear your command, of course, and then maybe they'll subdue the music while you're speaking. But then when you're done speaking, the music comes back at full volume. And then until the server actually processes your request, the music keeps playing, and then finally it gets an action or an instruction from the server to replace that music with something else. And I've actually noticed that with lots of different digital assistants. They just don't work very well that way. Alexa works very well in this way. It actually hears your command. It knows that the likely action is that the currently playing music needs to be paused. So it goes ahead and pauses it until the command interpretation comes back and the next action executes.
Interesting. So it prioritized that path instead of the status quo of continuing playing. I could see that. I could see the logic on that.
Yeah, it works pretty
it's
well.
Interesting how, again, we're trying to replicate human-to-human interaction where there's very little processing delay. And in this case, you do have to communicate to this outside server somewhere, which, again, modern internet connectivity makes quite fast. You then have to activate all these computers to do that processing, which, again, typically is quite fast. But it does add additional delay that in a lot of these human style interactions, even just a little too much delay starts to feel very weird and very non-human to us. And so engineering has to do a lot of work to get this right.
Yes, it is. It really is a lot. Okay, so let's go back to the weather example. So let's say the user said, what is the weather today in Tokyo? Well, of course, that's going to go through the ASR. It's going to come out as text. It's saying, what is the weather today in Tokyo? It's going to go through the natural language understanding system. That's going to understand the user wants the weather, the time is today, and the city is Tokyo. And then that gets dispatched to an internal component, really another set of servers, that has the current weather information in a database that it can query, look up what the weather is in Tokyo, and then formulate a speech output that the device will speak. And this is different from streaming music, where the streaming music is actually just a music URL that goes back to the device so music starts playing. There's a little more to it than that. There is actually some speech that's a preamble for most music playback. But in this case, for weather, it's only speech output. And now the system has to do something again, which is ASR in reverse. So instead of taking speech and turning it into text, we need to take text and turn it into speech. And this is called TTS, text to speech. And it's very interesting because it took Amazon lots and lots of time and money to create what was at the time a really beautiful, human, natural sounding voice from a person whose name is Nina, actually. And this person recorded tens of thousands of phonemes into a microphone. And then the original version of Alexa's TTS would construct words and sounds from these pre-recorded phonemes by taking the requested text. Like in this case, for example, the weather today in Tokyo is sunny with a chance of rain at 2 p.m., right? So it would take that text and turn each word into a set of phonemes and pauses between words in English, and then that would then get rendered into an audio file, which could then be sent down to the device to speak. So this was labor intensive, it was capital intensive, and it was also it was like 90% good. You know, it sounded pretty good.
Yeah.
This evolved, though. And over time, the Amazon engineers were able to identify more advanced mechanisms for training models that could actually take text and turn it into these speech patterns without requiring all the phonemes to be manually stitched together in the output. And this was actually a neural net. They called it neural TTS, and it sounded so much more natural and beautiful. And just as kind of a modern take on this, now you can go sign up for like $10 a month at one of these generative AI systems, and you can record a few minutes of your own voice, and then it can speak anything you want, and it sounds just like you. It's actually amazing. So what used to take months or years and hundreds of thousands of dollars of labor can now be done for $10 a month.
Yeah, that is just crazy. Yeah, another example and a theme in these conversations about exponential increase in the computation capability, and then just the more sophisticated tools we can build on top. And now to these generative tools that are just trained on large quantities of data and can produce effectively the result you would expect because they've been trained on the diversity of data needed to essentially cover all the cases that matter without having to be directly programmed to do so. It's remarkable.
It really is. And, you know, at the time when Alexa was first launched, it spoke English only. And then it got British English shortly thereafter and German shortly thereafter. And I think we got to like 10 or 15 languages within about 4 years of going live. Well, now if you go to one of these generative AI systems, like the one I'm familiar with is called 11 Labs, they launched last year and they support 28 languages. And you only have to give it about 60 seconds of your speech to get it to say anything you want in your voice.
Yeah, that's crazy.
It really is amazing. And, you know, I like to think of Alexa as like a pioneer in this space. In fact, there was a company that Amazon acquired whose name I can't remember at the moment, but they had offices in Poland and they did a lot of the work there, and just really, really impressive work. Because you remember the just absolutely terrible text-to-speech of the 80s and 90s and early 2000s. Like, it was just, it was fun to make fun of it, actually, because it was so bad.
Right.
And when Alexa came out, it was just beautiful. And people really thought Alexa was so natural and human. So much so that Alexa would get, on average, like 500 marriage proposals every day from its users, which is kind of funny.
Yeah. And this is the way a lot of these technologies came out, is very much done by hand and done as well as could be done, but which wasn't great. And it's just crazy over our lifetimes to have seen how they have really crossed the chasm from very clearly computer generated and computer executed to it's hard to tell if there's a human or a computer on the other side of the line in a lot of these cases now.
Yes, it's true. And the same thing's happening with video.
Yeah.
In fact, the next amazing leap here has been that you can record a video of yourself speaking, and you can feed that to an online service. I'm aware of one called HeyGen that will take your video and your audio, and it will translate it into any language you pick. I don't know how many languages they have, like 30 or 40. It will recreate that video of you speaking in your selected language, even to the point where your mouth and lips make the shapes you would expect to speak in that language. So it does not look dubbed. And I'm like, boy, have we come a long way in the last 10 years. It is just incredible.
No kidding. Yeah, that's wild. So I had one other back to Alexa topic, if we've got a couple more minutes. And that was, so we talked about how especially sound and speech recognition are imperfect. So what happens if I am speaking, and this has happened in the past, and I say something that apparently sounded like the wake word, but I did not intend it to be the wake word? How do these systems handle that situation?
Yeah, so first of all, tons of research and effort goes into making sure that doesn't happen, and that's called a false accept. This is where you speak the wake word, you don't speak the wake word, but Alexa thinks you did. There's all kinds of machinery built into Alexa, both on the client side and server side, to detect that nothing, that it looks like it was non-Alexa directed speech after that happens. And when that happens, Amazon goes to great lengths to discard that information, because they want nothing to do with recorded audio that has nothing to, that wasn't intended for them. And they did a really good job with it. Like the device closes down really quickly, the audio, when that happens. The other variant of that is called a false reject. And this is where you're saying the wake word, but it can't hear you. And those are really, really hard to detect because the device just doesn't wake up. It doesn't listen.
Yeah, the whole data minimization and privacy side works against you in trying to collect the data needed to solve that problem, or even to know that it happened.
Exactly. So the only way to solve that problem is to collect enough samples of training data where people have said the wake word in enough different noisy environments that you can get reliable detection.
Yeah, to sort of cover the domain, as we would say in the machine learning world.
Mm-hmm. But yeah, there were several layers of safety nets against the false accept problem, including a team that I worked on. We actually built the final safety net layer where it was like, okay, if the device said it was a wake word, and then ASR thought also that it was a wake word, and then NLU thought that it got something, but in the end, there's actually nothing to do here. My team actually built a machine learning model that would take a whole bunch of different input signals from the interaction to determine, actually, no, this is not meant for us. And we would detect a handful, but a lot of the first 2 or 3 safety nets actually did a really good job of stopping those.
Yeah, I can imagine. Well, that is very cool. So to summarize, the device really is, it's a computer, but its main job is that it's it's a microphone listening for one thing, and then it currently delegates all other processing to the servers in these data centers, what we call the cloud. And then they're really where the brains are in terms of figuring out what you said and what you meant and sending the response back. Do you have any insight if there's going to be a shift in this architecture to more of the processing happening client side, like in the device itself over time?
Yeah, in fact, that shift is happening for better user experience, because when you say something like Alexa stop, you really don't want to wait for that command to go all the way to the servers and back. And so there were some commands that could be interpreted directly on the device just for speed. But there were other use cases as well, like the automotive use case where you might be driving through a tunnel and you still want the device to work. And so actually there was a whole bunch of work that went into putting a very like some of the most popular what we call utterances or commands to be processed directly on device if possible.
Okay. And I can imagine that trend will continue over time because the experience is better, like you said, both for latency and for connectivity.
The experience is better, but it is harder to work with because doing over-the-air updates is more time-consuming and risky because you have to change the device that's out of your control compared to doing updates on servers that are running in data centers that you can directly manage.
Yeah, that makes sense. Well, cool, Dave. Thanks for walking us through. Anything else we should talk about to wrap this up?
I don't think so. I hope it was informative and useful.
Well, I certainly learned some things. So thanks again, as always. This has been a lot of fun, Dave.
Yeah, thank you.